Does memory affect every pipeline stage? Indirectly, yes. Where memory hits hardest, instruction fetch, code not in cache, load or store stage, data not in cache. So there's a code and data cache in L1 cache, remember, and also that's being propagated in L2 and L3 cache. So this is how memory affect the pipeline stage. When memory stalls, execution stage waits, write back waits, pipeline bubbles from. So when memory stall, the execution or the backend waits, the write back waits or the actual writing to the register, and the pipeline bubbles from. Think of memory as feeding the pipeline. If the feed is slow, everything slows. Why random access cause cache misses? Caches are built on temporal locality, recently used, spatial locality, nearby addresses. So a random address like a branch prediction, especially if it's not predicted accurately, will propagate a lot of misses. And as we saw, those are node structured. Therefore, the that could be spread jumbled in memory, if you know what I meant. Basically, these storage column is take advantage of a contiguous memory. Therefore, they are able to take advantage of this recently used and spatial locality. Now, random access breaks both node to next, then node to next. So each node could be anywhere in memory, likely not in cache. Result, cache means memory stall. Why branches plus cache misses are related? Branches don't directly cause cache misses, but branch mispredict to new code path to instruction cache miss, pointer heavy code to data cache miss. So this is what happened. The branches plus the cache miss are related because if you mispredict, you will need to get the new code path, and the new code path it means instruction cache miss or the instruction part of the cache or the L1, L2, 3, L3 cache, and the pointer heavy code will have a lot of data cache miss. So branch heavy code amplifies cache problems. So this pointer heavy code could also be thought as what the amplifier of the cache problems because the longer your chase or the more random and the heavier your code is, the more data cache miss you get. And the instruction is not as much as the data that you would point to along the way in node data structures. Is pointer chasing same as branching? No, but they are both pipeline killers. Pointer chasing, data dependency, branch, control dependency. Pointer chasing, cache miss risk, branch, pipeline flash risk. Pointer chasing happens in trees, branch happens in conditionals. Pointer chasing example B3, node equal to node 2 children, argument I, semicolon. Address unknown until runtime, memory fetch stalls pipeline. Cannot be free fetch well. So because it's pointer chasing, the address is unknown until runtime and memory fetch stores pipeline. Unlike with modern CPU today, actually they predict like many steps ahead the code stream. So for pointer chasing, you won't be able to know or you can that be steps ahead because the address is only known at runtime. Why B3s and LSM3 suffer? B3, nodes scattered in memory, pointer chasing, unpredictable access. LSM3, good for writes, reads still involved. Multiple SS tables index lookups pointer the references. Both are latency oriented, not throughput oriented. So they're not throughput or they're not maximizing the number of execution that the pipeline could get. They are both latency oriented towards the front end or towards the customer. That's why the Firestore and B3 are almost instantaneous in the front end, but not necessarily maximize all the CPU resources of the back end. Why column store wins? Column store scan contiguous memory, predictable access, few branches, compressed data, SIMD friendly. Pipeline view, every stage stays busy almost every cycle. Final mental model, lock this in. Branch mispredict flashes the pipeline. Cache miss starves the pipeline. So this is a important distinction with branch and cache with regards to pipeline. The branch flashes all the pipeline. The cache miss starves the pipeline. It means there's a lot of bubble with cache while branch mispredict like flashes the entire pipeline. Column stores avoid both by turning queries into tight, predictable loops. Once you see this, inside the machine, DDIA and real database engines finally line up. What run length encoding really is at CPU level. Plain definition. Run length encoding compresses repeated values by storing value, comma, count instead of value. Example, column store, original column, store underscore sk colon. You have 3, comma 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 3. RLE from, so we will see 3, comma 10. So we have 10 trees. That's what it meant, 3, comma 10. Why RLE is perfect for CPUs? RLE turn this for I equals 0, semicolon I less than 10, semicolon I plus plus, opening semi-curly bracket, if store underscore sk, argument I equal to 3, count plus plus semicolon, closing semi-curly bracket into this. If value equal 3, count plus equal run underscore length semicolon. CPU advantages without RLE, many loop iterations. With RLE, few iterations. Without RLE, many branches. With RLE, almost no branches. Without RLE, many more loads. With RLE, one load. Without RLE, cache misses. With RLE, cache friendly. So you can see one load because it compresses it. Almost no branches, few iterations, cache friendly. RLE reduces instruction count and memory traffic. That's why it feels like lowering instruction count because it literally does. So when you load the instruction count, you also load the memory traffic, right? Because you increase what you could accomplish in one compressed byte than you would have done if you did not like 8 times difference, 8 to 10x difference. Second, why CPU predicts branches at all? The core problem, CPU are pipeline. Pipeline example, fetch to decode to execute to memory to write back. So this consists of one cycle of a CPU. It needs to fetch, decode, execute memory, or write back. This happens in just one cycle of CPU. And remember, the cycle of CPU is just zero point 0.5 nanoseconds, like 100x difference with memory. Now a branch break this. If x is greater than 10, go to A, else go to B. The CPU must decide which instructions to fetch next before knowing the result. So that's why it needs to predict. If it waits, pipeline stalls terrible performance. That's why we have this, in the modern CPU, they actually have this dynamic uh, tracker that allows it to track the most recently used um, instruction that will likely be executed to predict. That's why they also less likely to miss because those cycle or those stalls are important because the CPU would stop working after that, right? And the time, the time always move forward. So you need to you need to you need to consider that because if not, your app will not become responsive. So CPU guess predict the CPU. First, look at past behavior of that branch. Second, predicts taken or not taken. Third, continuous execution speculatively. If right, pipeline stays full. If wrong, pipeline flash, branch mispredict penalty. So the taken and not taken, the parallelism are also included there. Based on the past behavior, could it be executed in parallel? And if it is, we will execute this out of order and then we will just put it back in order after the execution before we return it to the programmer at the store register file. So that's what's happening in details. So if wrong, pipeline flush, branch mispredict penalty. How CPUs actually predict branches. This is not OS, not multi-core, not cache coherence. This is pure microarchitecture. Simplest predictor, early CPUs. Last time this branch was taken, assume taken again. So it's kind of like with OS, but it is being done in CPU, right? So it's the same principle. Stored in branch history table. That's actually what it's called in the real microarchitecture BHT. Slightly smarter, 2-bit saturating counter states strongly taken, weakly not taken, strongly not taken. So this the 2-bit saturating counter is how the CPU would decide if it will use it again. This prevents flip-flopping on loops. Modern CPUs, global history, per branch history, pattern tables, hybrid predictors, all of this is transparent to software. So you can actually see this in your actual OS or BIOS. Where is this inside the machine? You're not crazy. You have read parts of this, but it's split across chapter. Must read chapters, high ROI, chapter 3, pipeline execution. This is where pipeline stalls, control hazards, branch penalties are introduced. Read this chapter now that you know why database care. Chapter 4, superscalar execution. This is where speculation, multiple instructions imply branch prediction necessity and parallelism becomes clear. Chapter 5, the memory hierarchy. This is where cache misses, memory stalls, locality connect directly to column stores compression RLE. What the book does not explicitly say, inside the machine does not talk about column stores, bitmaps, RLE in databases, but DDIA connects those ideas to what these books explain about CPUs. You're doing that integration now. That's why it feels hard. Why RLE avoids branch misprediction? Compare without RLE for each row colon. Next line if value equal 3 dot branch executed per row unpredictable data branch mispredicts with RLE for each run colon next line if run that value equal 3 That means branch per run, predictable, stable loop structure. This is why column stores run at memory speed. Did you already read this? Sorry, with RLE, we have for each run, if run that value equal to 3, which means that we execute branch per run. It's predictable, stable loop structure because it's contiguous. And this is why column store run at memory speed. For branch, it's a branch executed per row. Unpredictable data per row and branch mispredicts. Now, did you already read this in the pipeline chapter? Yes, but only abstractly. You read branches causes pipeline flashes. Memory stall hurt performance. What you didn't yet have is a real system, Vertica, BigQuery, a reason they designed storage this way. Now it clicks. Database storage layout exists to feed CPU pipeline efficiently. Final mental lock-in. RLE is not about saving this space. It's about being unpredictable, about turning unpredictable row by row logic into predictable CPU loops. Once you see that, bitmap encoding, predictable pushdown, column pruning, SIMD execution all become inevitable, not mysterious.